Hey all, in this video we are discussing applications of Laplace transform. Today we are discussing the application of Laplace transform to solve the integration values, and next video we will discuss the application as solution of ordinary differential equations. Okay, so first consider a problem using Laplace transform. Evaluate integral 0 to infinity t into e raised to minus 3t cos 2t dt. We have we have the definition of Laplace transform. L of f of t equal to integral 0 to infinity e raised to minus st f of t dt. Comparing this equation with this, we can get s equal to 3. Here e raised to minus 3t, so s equal to 3, and f of t equal to t cos 2t. Then integral 0 to infinity t cos 2t e raised to minus 3t dt is equal to, we can write L of t cos 2t. This is the definition of Laplace transform of t cos 2t. Here we use the method of multiplication by t. And the method is minus 1 raised to 1 into d by ds of L of cos 2t. We know that Laplace transform of cos 2t is s by s square plus 4. Then next step we take the derivative with respect to s. Next step we are cancelling some terms or adding some terms. We get s square minus 4 by s square plus 4 the whole square, where s is equal to 3. Then substituting 3 in this equation, we get answer 5 by 169. Next, consider next problem. Using Laplace transform, evaluate integral 0 to infinity sin at by t dt and integral 0 to infinity e raised to minus at sin at by t dt. We know that Laplace transform of sin at is L of sin at equal to a by s square plus a square. Next step, L of sin at by t. Here t is missing. Sin at by t is equal to integral s to infinity L of sin at ds. Division by t method. Okay. L of sin at by t is equal to integral s to infinity L of sin at ds. That is equal to integral s to infinity. We know that L of sin at is a by s square plus a square ds. Here a is constant, so take outside, and integral 1 by a square plus s square ds is 1 by a tan inverse s by a. Substitute that value. Then next step, substituting the upper and lower limits, we get pi by 2 minus tan inverse of s by a. So pi by 2 minus tan inverse of s by a is cot inverse of s by a. So L of sin at by t is equal to cot inverse of s by a. That is integral L of sin at by t. Here we are substituting that the definition of Laplace transform. Integral 0 to infinity sin at by t e raised to minus st dt is equal to cot inverse of s by a. When s is equal to 0, put s equal to 0, we get integral 0 to infinity sin at by t dt e raised to minus st becomes 1, e raised to 0, that is 1, equal to cot inverse of 0, that is equal to pi by 2. Therefore, integral 0 to infinity sin at by t dt is equal to pi by 2. First answer. Then next, put s is equal to a. Integral 0 to infinity sin at by t e raised to minus at dt is equal to cot inverse of a by a, that is cot inverse of 1, that is pi by 4. Therefore, integral 0 to infinity sin at by t e raised to minus at dt, the answer is pi by 4. Here we are giving some problems. Do yourself. Okay, thank you.